All right. So let's see. Um, now, I mean, of course, it's nice to see the order of you doing the multiplication among all three matrices. In a sense that if you're trying to multiply matrices A, B, and C, as long as they're compatible in that particular order, that A goes first, B is the middle, and C is the third one, then it won't matter if you decide to multiply A and B, then multiply the product of A, B, and the C, or if you somehow decide to multiply B and C first, right, then multiply the A with the product of B, C. But you have to make sure that if C was multiplying with the B from the right, then whatever you do later on, then C has to be always to the right of the B, because the order of the matrices in multiplications actually will matter. That's what I'm going to get to in a second. Distributive property. So if you thought that seemed trivial, why would you write two occasions that they seems the same, right? I mean, yes, they are redundant if A, B, C are numbers. But if they are matrices, do you see that if you distribute the A, over the addition, the A has to hit the B from the left. The B is multiplying with the B, A is multiplying with the B on the left. And also, if somehow C shows up on the right-hand side of the sum of the two matrices, then you distribute the C, and C has to be always multiplying with the A and B from the right. Now the third one, then again, it's sort of associative property, right? But since the little c is a constant, right, a scalar, so that makes the whole process, easier, right? But anyway, we have a couple things that I want to alert our students when it comes to matrix multiplication, starting from number one. So in general, so you should not expect that the product of two matrices, A and B, is the same as, the product of BA, right? So order does matter. So what I can do is, I'll demonstrate with, a few easy matrices. Say this is number 1, 2, 3, right? So in the first bullet point, so let A be a square 2 by 2 matrix. 1, 2. Now again, feel free to take notes or take pictures. But I guess you can tell how I put them on the packet. So they're just something that you can just read and understand, and I don't think they will be on the test in any way. 2, 1, 0. So we can easily compute, right, the matrix product. If you want to type it up, if you were to try it, right? But I'm going to do it by hand, again, just as a quick review, how the matrix multiplication works out. Now, as always, ask yourself that if the two matrices do multiply by checking their orders. Since they're 2 by 2, right? So they do multiply no matter what, and you should expect also a 2 by 2 matrix, right? Now, you will find all the entries, right, after multiplying the two matrices by going through the rows and columns, say starting from the first row, first column of the product. That should come from the first row, right, quote unquote, multiplied with the first column, right, of the B matrix. And the way you multiply them is you go by entry, right, from the corresponding, position in that row or the column. So it will be 1 times 1 plus 2 times 2. So that you get your 5, right? So then you go to the next one, the first row, but the second column. So you will need the second column from the B, right? And it's going to multiply with the first row of A. So that way you get A 1 times 1, but 2 times 0, right, added to be 1. Right, so then you do the same thing, but now go into the second row of A and let it get together with the first column of the B. That's going to get you the entry on the second row, first column in the product, right? So 0 times 1 is 0, 1 times 2 is 1, 1 times 2 is 2, right? So that gets you a 2, right? And the last entry, so you just go with second row, second column, right? Second row of A, second row, second column B, A would be a 0. So if you do the same thing by swapping A and B, then compute B times A, and it will still be a 2 by 2, right? And that's going to work out as 1, 3, 2, 4. Okay, so again, obviously, they're not the same. Okay, well, is it possible sometimes that AB are the same as BA? Yes, right, but it's not guaranteed. So therefore, we say the matrix multiplication does not preserve the what do we call it? The commutative property, right? So you expect that from numbers, but not from matrices. Anyway, so moving on to the second bullet point. So if you have a product of A and a B, then it's the same as the product A and a C, right? So in a number sense, as long as that A are not 0, right? A is not 0, then you can cross it out, right? And you can simply conclude that B must be the same as the C. But not true in general for matrices. So for example, let's take A to be 1, 0, 0, 0. B, that will be 0, 0, 0, 1. C will be 0, 0, 0, 2. Okay. So you compute what AB is, right? So that's pretty simple. Whole bunch of zeros. And it turns out that the product of A and B is a 0 matrix, right? But do you see that's indeed the fun part, right? Or I mean the confusing part. A and B are not 0 matrices, but their product is a 0 matrix, right? Can you think of any numbers who are not 0, but the product of them, are 0, right? That will never happen, for pure numbers. And obviously you can compute A and a C, right? And you'll find, again, it's a 0 matrix. But obviously, right, actually B and a C are not the same. Okay. All right, last one. If the product of two matrices is 0, and we have something called a 0 product rule, right? The only way it works for numbers is that either number must be 0 or both of them. But for matrices, that might not be true. Okay. So what we can do is we'll take the same matrix A from the previous occasion, and the B again the same as before. Obviously, A times B is 0, but neither A or B is 0. Okay. And again, that's just something that you should always alert yourself when you try to play with the matrices. Okay. So matrices are numbers, right? But maybe in a different dimension. Okay. Anyway. Now, as for the matrices, well, of course, we still have some matrix to deal with in 9.5, but not as intensive as what we did in the first 3 topics. So I mean, just in case, if you're looking at stuff on the review packet, right? That chapter 9 review packet. the one that has 38 questions. So if you get question 9 or something like question 19 on the test, I mean, it could be either MCQs or FRQs. If it's MCQ, you guys all know how to type it up and do it in a calculator, right? Or I mean, maybe you don't even you don't even feel like type it up because it might just be that easy, right, to do it. But my question is, if it's an FRQ, right? Do you know what you have to show me to get all the full credit, to get the full credits? Not only the right answer, right? Write down the matrix, show me that you're adding entry by entry, right? Or doing whatever you're supposed to do when it comes to, let's say, 2 times A, right? The scalar multiplication, because like I said, I need to see something to convince me that you've learned the new stuff, right? If you do that, right, with the right answer, then you guarantee the full credits. All right, so the same thing for 21, right? I mean, for this kind of problem, I think that it's more desirable to do it in a calculator, right? Unless you have to show me the work. But always ask yourself, how do I do it by hand, right? Show all the steps. Okay, so there was an example typed up, right, in the packet, which you don't have access to in the test. All right, please remember that. Now, matrix multiplication, then I highly suggest that you do it in a calculator, right? Whereas multiple choice in FRQ, get the answer correctly, okay? Because you see how easy to make a mistake. Even it could be just 2 by 2, right? Times the 2 by 2. But also be open to the possibility that matrices might not multiply at all, right? It's fairly possible. Not saying this one, but I'm saying, in general, they don't multiply sometimes. If it's FRQ, make sure that you show me how row and column get together. Show me some work, right? Not that say you have to show me exactly what I did in class, but I need something that's relevant to your answer. Oh, sorry, not that one. That's all right. Now let's move on to 9.5. And the reason why I didn't give you the 9.5 packet at this point is I do want to make sure that you learn something that's more than just knowing the formula, because you will know it anyway, right? You will find a way to remember it, since we're testing you guys next week. So what we're going to look into in the next probably 10 minutes is how do we solve a linear system in 2 variables. So what was your favorite way so far? Matrices? Oh, I thought that most people like addition, elimination method back then. No? Oh, good. Because I think that the matrix is the ultimate way, right? Now, of course, things get pretty tedious with the matrix, right? Now, for 2 by 2, sometimes it's probably not worth it, right, to put in that much effort to get the matrix done. Not to mention sometimes the systems are pretty easy. But at this point, you see that we're trying to raise the level to somewhere beyond just the high school algebra, right? So let's figure it out how to in general solve a linear system with A, B, C, A1, B1, C1, A2, C2, B, A2, B2, C2. They are constants, right? They could be any real numbers, right? I just didn't explicitly specify what they are. I believe that it might be cleaner to show you how to solve these 2 equations using what they call addition, or some books refer to it as elimination method. Okay. So what we need to do is we need to eliminate either x or y from the two equations, but I need to match their coefficient before I do that, right? Let's say I want to get the x solved first. So I need to get rid of the y. But there's no reason why b1, b2 are the same. So what I can do is I'll multiply equation 1 across the board with a constant b2. All right, so then you see that the first term is going to be a1 b2, right, times x. And by the way, so those uppercase letters are not matrices, just numbers. Plus here b1 b2, right, equals, let's go with the alphabetical order. So b 2 c1, right, so I'll call that equation number 3. So now to match the coefficient of y in the second equation, I need a b1, right? So why don't I just multiply the second equation across the board with not just b1, let's make a negative b1, because we like to add instead of subtract. So now the first term, keep track of the signs. It will be negative, right? a2, b1, and here you get negative. Oh, sorry, there's a y there, right? So that's negative b1, b2, y, right? And you get negative b1, c2, right? And that'll be, say, equation number 4. And since we call it addition, right, or elimination, so we add to eliminate the y, right? So we do that term by term. So those two are gone. You're left with a1, b2 times x minus a2, b1. Oh, why am I missing those variables? All right, so a2, b1, x. You factor out x, you get a1, b2, oops, minus a2, b1, right, times x equals, the right-hand side will be b2, c1, minus b1, c2, right? And we get x just by dividing out the coefficient, right? It will be b2, c1, minus b1, c2 over a1, b2, minus a2, b1, okay? Now, and again, we're supposed to know those numbers, right? From A to C, right? So when we plug it in, you get an easy number for x. Then how would you solve for y once you get an x? What do you think? Right, so you take the x back into any equation to solve for y, right? You could do that numerically, but if it's pure algebra, it gets, kind of tough, right? But here's a better way to just read out the answer for y by inspection, right? So let's see how comfortable you guys are with that little trick. So let's take a close look at these two equations. Say number 1. So I happen to notice equation number 1 has a very interesting symmetry, even if we do some changes. And the kind of change I'll do is I'll swap x and a y. But at the same time, I'll swap a and a b. Can you guys all picture a new equation in your head? Once I replace x with a y, y with an x, and also I replace a with a b and b with an a. Will that equation look the same as before? It does, right? Let me put it down. So I will interchange x with y, and a with b. So see what the first equation reads. When I see a, I put b, right? But still b1, right? So a1, 1 still there. b1y plus, right, a1x equals c1, right? Well, of course, the order was a little bit different, right? But you do have to admit that it's the same equation. If you do the same thing to the second equation, you notice that second equation has the same property. Later on, you probably heard people saying the equations are invariant. Invariant means that it's not changed, right? Invariant under interchange of x and y, a's and b, right? So that's a very important property. And it turns out that in our universe, thanks to those invariants that we have, you might not heard of, there's something called conservation law. Have you guys heard of conservation of energy? Right. So physicists know this, and she was a female physicist. So she was probably back in the 19th, 18th century, right? Very smart female physicist. Her name is hard to pronounce. I think she's German. Emmy Noether, if you look her. Right. So she figured that for every conservation law in the universe, it corresponding to a invariance or a symmetry. So people sometimes don't tell any difference between invariance or symmetry. So for energy conservation, turns out that there's something called a time translation symmetry or invariance. It sounds pretty fancy. It's as simple as you do an experiment right now. And if you do the same experiment the other day, the result's going to work out the same, right? It makes sense, right? But guess what? That kind of an interesting, but you take it for granted, right? That kind of a symmetry because time translated, right? From now to the future or from the past to now, there's a conservation related to that. But anyway, so the equation has this kind of symmetry. What do you think is going to be about the solution? If the equations are invariant on the interchange of x and y, a and b, should you expect the same invariance from the solution? You think? Well, this is like you look into the mirror, you see that your face is symmetric, right? What about your dad looking into the mirror? You should expect the face looks symmetric. It's not about your face or your dad's face. It's about the mirror. The mirror preserves, right, some kind of a thing to make things invariant. So what do we get? Where do we get the solution from? The system, right? If the system doesn't change under certain, is invariant under certain changes, so do the solutions. Now, why am I saying that? Do you see that if I interchange x and y, can I write down the solution for y if I just look at the solution for x and I decide to say, whenever I see x, I'll put y there, interchanging x and y, right? Whenever I see b, I replace it with an a. I don't do anything about a c. So it'll be a2, c1 over, now be careful, right? So you're going to swap a and a b, right? So it'll be b1, a2 minus b2, a1. Oops. And it turns out that is indeed the solution for y, if you do it by hand, right? So that's why and how physicists or scientists figured out something when they couldn't even do experiments, right? They observe, they guess, and also hopefully someone else can prove them right? Anyway, oh, right on time. Before I let you take a break, I want to think just for a brief moment to see what we have accomplished. So that's a generic linear system of two variables, right? And we solved it once. But that means we have solved every single linear system of equation of two variables, right? There's no need for you to do any more problems anymore. And that's how we code or we model, right? That means if you have a linear system, equation solver, right? If you write a program, you can easily do that with any kind of language. All you expect that your user is going to type in, right, or put in those A, B, C, and the program is going to tell you what the solution is, right? But the problem is, if that seems like a fancy formula, right, that will help you for any kind of a equation, right, two linear equation, two variables, how do you remember it if you have to for the test, right? But anyway, so take a break, then we'll come back and take a look at how do we remember this kind of fancy formula. Timer for 10 minutes. Testing, testing. All right, so let's get started with officially with 9.5. The packet I just gave you has the first page, right, all typed up for some terminology or some prior knowledge you need to have about system of linear equations. Okay, and even though I was using the system of two equations as an example, but those terminologies or things that you should know about the linear system are the same, right? Whichever system you're looking at, right? You can have as many equations as possible. It's just that they have to be linear. So I want to focus on, some terms, and you might see them from some, special multiplications. So again, it's easier to imagine what the linear system look like if you go with the two-dimensional or the system of two linear equations. So each equation will be plotted, right? And they will be a line. So the first case is if the system has one unique solution, but as you know that solution has, two numbers, right? One for x, one for y. So that's a order pair, right, for a two-dimensional linear system. But as you can solve from the matrix sections, so you might have maybe x, y, z, right? They're called the three-dimensional system. The lines will be three-dimensional. Actually, not three-dimensional. It will be a three-dimensional plane, not a two-dimensional line anymore. And the solution will be order triple, right? So the triple is, a set of three numbers. But anyway, if you have a unique solution, the system is known as consistent. But the system also independent, as you saw that those two lines, those equations are different, basically, right? Because independent, right? It's like, you'll be an independent person, you'll be independent on your parents. Well, the thing is, people are not the same, right? So that's why they're individual students, right? We're all independent. But sometimes you might have two equations. They are similar, not exactly the same. Now, in two dimensions, the two lines are parallel. But the concept for having, a parallel or two parallel lines is they will never intersect, so there won't be any solution, and you consider that system to be inconsistent. Okay, but they're still independent, right? So the two lines are still different. You can tell that even though they have the same slope, right, but they differ by their y-intercepts. Now the last case, it seems like one line, but it's just that a line is on top of the other, right? So these two lines are identical. Well, they might still look a bit different, but it's almost going to be a common factor, right? You could cross out and realize that the two lines are the same. But basically, if you plot them, the two lines are exactly overlapped. You'll be having infinite many solutions, right? But as long as the system has solution, it will be consistent. Okay, but the system is dependent since the two lines are the same, right? So one depends on the other, or there's some lines, there's some equations are redundant. All right, so simply put, you have systems that are consistent as long as they have a solution, but they could have infinite many, right? So If they do have solution, either one or infinite many, the systems are consistent. If they don't have any solution, the systems are inconsistent, right? Now, when it comes to dependent or independent systems, all you have to tell is whether the equations, whether the lines, right, are identical or not. If you do have identical, equations or lines, they are dependent systems. Otherwise, still independent, even if you don't have solutions. Okay. All right. Now, let's moving on to that fancy rule, which you could certainly use to help you remember, how to solve a linear system in general, right? It could be a system of 2 equations, 3, even 4, or however many equations you have, as long as they're linear. But what we did, before the break was to demonstrate how things works out algebraically without knowing the fancy rule. But we only tried 2-dimensional system, right, just to make the demonstration a bit easier. But I want to point out, so mathematicians define something called this determinant, which looks like a matrix, right? It is still a M by M, right? In this case, we are expecting only square, right, array. So the number of rows and columns must be the same to be, calculable, right? So here we have almost like a 2-by-2 matrix, but you see the difference between a determinant, even with 2 rows, 2 columns, right, and a 2-by-2 matrix. We use vertical lines instead of square brackets. And that looks like absolute value, right? And indeed, in the future, if you learn a different course, either at college or in graduate school, they call it linear algebra or linear theory. They'll be talking about matrices and determinants. And it turns out that determinants are, technically speaking, the quote-unquote absolute value of matrices, just like you have absolute value for numbers, okay? But that is such a strange way to come up with a number out of a couple numbers, right? So you line up those numbers, right? You put them in a 2-by-2 array, right? And the way you compute that number, which represents the value of the determinant, is by cross multiplication, okay? But you have 2 diagonals, right? The one that starts from the top left to the bottom right is the major diagonal. And you take a positive, so A1, right, multiplied by B2, right? So cross multiplication happens on the first diagonal. You have a plus sign in front, but then you have the minor diagonal that starts from top right to the bottom left. You do A2, B1, right? They subtract off from, the first product. So basically, the entries multiply on the major diagonal, subtracting the elements multiplying on the minor diagonal, and you do have to follow this particular order, and it is a subtraction. Okay, and that's what we call determinant. Okay, it's a 2-by-2. You can have 3-by-3, n by n. Even though that there will be different ways of calculating those determinants, but at the end of the day, it is still the same, but they look different in different dimensions. So you might say, well, what's the point of learning that? Maybe you have noticed this is exactly the same combination that you saw right there on the denominator. Okay, so if you do the math like that, you're always going to get it, right? But if you try to memorize the pattern, do you see how easy it is to screw up, right, the structure? Because, you can very likely put the wrong order, right? Instead of putting A's and B's, you put A's and C's, right? Also, even though they're two indices, but whereas that you're getting exactly those indices in the right place, not to mention this negative sign. Okay, so I'll say that the formula seems powerful, but if it's not intuitive enough for you to memorize it, it's worthless. Okay, but there is a way to remember. That is to use something called determinant. Okay, so now let's say the rule called the Cramer's rule, which is obviously named after the mathematician, right? Whose name is Cramer or Cramer. He said that if you're looking at a 2x2 linear system, if you line up the variables and having the constants on the other side, just like you would to do for any kind of linear system using the matrices, you could write down 3 determinants. Okay, the first determinant, we're going to call it D. And the way to get it is just by extracting the coefficients of x and y, right? Just like, you're getting the first couple columns of an organic matrix, right? As soon as you line up the x and y's. Then you need to build 2 more determinants, one for x and the other for y. And we use uppercase letters to let you know that they are not, those little x and y, they're not variables. They're just some peculiar ways to come up with numbers out of those coefficients and constants. But I want you to notice how to build the matrix, the determinant of x based off the matrix D or determinant D. As you notice that matrix, keep saying matrix, determinant D and the determinant x share the second column, right? And the determinant D and determinant y share the same column, the first column. That means you should build the x just by looking at the determinant D. But how would you know that you should replace the first column and the D with those constants? Here's how I usually remember it. There's a reason why I'm calling it the x determinant. Determinant. You're trying to find out a way to determine what x is, right? I guess that it deserves to be a bit special when it comes to the first column, since the first column are dealing with the x. And the way you can make it a bit special is take the constants on the other side and update the first column for the x determinant based on the D determinant. Or you don't touch the second column since that's all about the y. Okay, we're not getting to the y, so we'll make something special happen to the first column. Okay. Now the same logic applies to the y determinant. So if you will keep the first column in the D, right, and we'll replace the second column, the D, with the constant C1, C2, and that means you are going to get something about the y, right, out of this determinant, right? So something special happening to the second column. All right, so once you have all 3 determinants, the way you calculate them are exactly the same. Do the cross multiplication, know that the elements multiply from the major diagonal from top left to bottom right, subtracting the other diagonal. Okay, and once you get the value of the determinants, you divide the x determinant by the D determinant to get the solution for the x, and do that for the y. All right, and that's how you get the solution. Like you saw, we did that algebraically, right? So it's pretty much like, translating the kind of an algebraic way to more like a graphical, visualized way for you to remember how those coefficients and constants go into certain places to get you the solution, right? Without memorizing, the certain kind of, algebra you have to do, right? Because we've done it, right, once forever. So we just need a way to remember it. And also, it's actually kind of powerful, but not as powerful as matrices. So the Cramer rules does tell us a unique solution, or sometimes, you might not have any solution or infinite many. Okay. So here we have sometimes a determinant D which happen to be 0. And I hope that you realize at this point why we call it determinant D. D stands for the denominator. That's why it always goes to the denominator, right? So now if the denominator, right, determinant is actually 0, so that should alert you that there's something wrong, right? You have a 0 denominator, so you can have either undefined, right? But as you know, most of you will go into calculus in the fall, you'll be getting a lot of problems asking to evaluate what's going on with 0 divided by 0, right? And that's actually not always undefined. Okay, you can get something meaningful from 0 by 0, but if you're looking at something non-zero, say 1 over 0, and that's indeed undefined. Okay, so there's a big difference. But you see that if you happen to get a 0 D determinant, it will be either of the two cases. Now, if you notice by computing the X determinant or the Y determinant, they work out non-zero. That means you divide a non-zero number by a 0, then that's indeed undefined, which means that you couldn't find any solution for X. And therefore, Y is automatically undefined, right? So that means you get no solution for that system. And that's just a fancy way to write it, which you don't have to, but you need to know what they mean by that. But now, what happens if we have a 0 D determinant, and also the X and Y determinants are also 0? And that's probably the weirdest case, right? 0 by 0, well, at this point, of course, you might want to just go with, the conclusion, right? It refers to the infinite many solution, even if it doesn't tell you what those solutions are, right? But you should be able to find maybe from multiple choices that becomes, this case that you have infinite solution. And also for a two-dimensional system, it is possible for you to even write down some kind of solution just to capture the relation between X and Y, even though you're still getting infinite many solutions. But sometimes they do want to know that there is a way to specify what the solution will look like. But it seems as easy just by taking one of the equations from the original system, right? Whichever you like, either first or second one, and just sticking here, say that we're going to build a set of infinite order pairs of X and Y, and vertical bar is a condition, right? So we'll put those X and Y such that they satisfy the equation. And the reason why it doesn't matter which equation you pick is, remember that a dependent system has infinite solutions. But being dependent means that the equations are redundant. They're the same. So whichever equation you pick, because they will be the same anyway. All right. So now let's give it a try, right? With a 2 by 2 or a linear system of 2 equations, because even just by calculating by hand, the determinants are super straightforward, and we'll see that how things works out. Not just in the most traditional sense that you get a solution. What if you don't have a solution or infinite many? Anyway, so as you can see that in letter A, the variables are lined up, the constants are on the right hand side, so you can certainly extract the D determinant, right? 3, 6, right? -2 and a 1, and go ahead and calculate what it is, right? Remember, do the cross multiplication. So you do 3 times 1, right? But minus the order diagonal, -2 times 6, okay? And that'll work out as 15. And you don't have to do mental math, all right? So if the numbers are kind of ugly, use the calculator. So now let's build the X determinant. Now, can anybody tell me what number should I put for the first column of the X determinant? All right, if I zoom out a little bit so you can see how we built the X determinant, right over there. We keep the second column, right, of the D. We'll replace the first column of D with constants, right? Therefore, we'll put -7 and 6 over here. We'll keep -2 and 1 as before, okay? And go ahead and calculate what the X is. Be careful with the signs. -7 times 1 minus -2 times 6, right? What is that? -7 plus 12, so 5, right? Now let's do the Y. I guess you get the gist. So we will keep the first column of the D. We'll replace the second column with constants -7 and 6. Okay, and we'll do 3 times 6, okay, minus -7 times 6. All right, so that'll be 18 minus -42 plus 42, so it'll be 60. All right, there you go. All right, so if you just refer to the Cramer's rule, X will be the determinant X divided by the D determinant, right? So it'll be 5 over 15. That works out as 1/3. And Y will be the Y determinant over the D determinant, right? So it'll be 60 over 15, so that's a 4. Okay. And that could be, an FRQ, right? But how do you feel about the Cramer's rule? It's okay, right? Very doable. But how do you like it? Okay. But I guess that the D determinant is fine, right? Line them up, get the numbers. But I guess that people tend to forget, hey, which column do I choose, right? Or change, right? Yeah, that's probably the only part that people don't like it, right? Now, let's say honestly, I'm not a big fan of the Cramer's rule, right? Simply put, that it's not very realistic. By realistic, I mean, ultimately, right? If you're gonna be, remember that last time I showed you how to model the traffic flow, right? Using the linear system, right? I mean, you see how powerful the matrix are, right? I mean, now this is like, if you wanna teach your little sibling in the summer something fancy, right? So if they're already in the 4th, 5th grade learning the system equations, right? You say, well, you know what? I've been struggling with addition, subtraction, addition methods or substitution methods. You know what? You can blindly follow the rule. You teach them how to follow the rule, right? I guess that's in general what you want to do with them. Follow the rule, right? Get it right. That means they don't have to know anything about algebra, just simple math. And also, I guess that's a good way to check if they can do those multiplications, right? But first off, in real world, there's so many variables. And you can look up on internet, see how complicated the Cramer rules can be when it goes to 4, 5, 6, or even 10, 100 variables. But matrix are still, easy for the calculator or the computer. Not to mention that the matrices tell us when you have infinite number solutions and what those solutions look like at whichever order. But the Cramer rule doesn't tell us that. It is powerful if you're expecting one unique solution. It tells exactly what it is, right? It does save you the hassle for remembering, changing the sign, play with, the algebra, adding, subtracting stuff, right? And also, it's so easy to make mistakes, right? If you do it by hand, even though it's 2 by 2. Not to mention, no one's going to really code the computer using the Cramer rule. So they're still going to go with the matrix. Yes. Mm-hmm. Exactly. So for our test, when it comes to the Cramer rules, it's possible they have to solve for 2 equations like that, or even 3 equations, which I'm going to get to in a second. But as you can see, if this is something that I have to seriously check to see if you guys get it, as an FRQ, what do you think is going to get the points for? Are you getting points for showing me those math? No, because I don't want to see those simple math, right? So you're functioning at the college level, right? What makes you different from your little sibling? You know how to set up the determinant, right? So I don't need to see the baby algebra. So I will show you how to do that in calculator. But if it's an FRQ, you need to tell me what those determinants are, set them up, then I don't mind, you just tell me what the answer is using the calculator. But you do have to show me what those determinants look like, right? And also refer to Cramer's rules to tell me what the answers are, okay? Now, when it comes to 3 dimension, it's almost impossible for people to memorize and get it perfectly done since there's so many numbers. Because can you imagine that a 3 by 3 determinant, there will be 9 numbers, right? And turns out there will be even more determinants. But what I expect is you show me how to set up those determinants. Then, since you have access to calculate the whole test, figure out what the determinants are, call on the Cramer's rules, and figure it out, right? There's no need to work on those tedious algebra by hand. Okay? Am I clear on the test? Now, something that you might want to do maybe later today, or if you, like I said, well, bring those packs with you if you're going to be on a trip to anywhere, right, in the next couple of days. So this is something that you want to try with the Cramer's rule, know what they are, right? How to write down the determinants, right? The D, X, and a Y, right? And figure out what little X and Y is going to be, right? So you need to convince yourself that for this problem, even though that you see the numbers are kind of ugly, and I scramble the terms on purpose. So you need to rearrange the terms, right, to line up the X and Y before you extract those determinants. And I'll tell you what those solutions are. So X is going to be 0.733, and then Y will be negative 0.755. All right, so make sure that everyone is able to get that. Okay, like I said, pretending that it's 7 for Q, set up determinants, use the calculator to figure out what they are, divide, and get you the X and Y. Okay. All right. Now, since Ariel says that, hey, what happens if there are more equations, right? Now with matrices, you can deal with more than 3 equations, but when it comes to Cramer's rule, the only level we're testing you guys in the test will be up to 3 equations. And therefore, we need a 3 by 3 determinant, okay? But just look at that, okay? So there's 6 terms, right? With all kinds of a combination of A, B, and C with scramble, indices, right? How likely that you'll be able to memorize exactly that formula? Well, this is why there's something else to help you to remember how to write down those terms correctly, right? But again, I was trying to make the point that when it comes to even a 2 by 2 determinant, I'm not interested in how you calculate it, but I do care if you know how to set it up. Does it make sense? Now, when it comes to 3 by 3, that's even more true I'm not very interested in you show me all that math because it's just simple numbers, right? Adding, subtracting, multiplying each other, right? It'll be tedious, and you will end up getting 4 determinants. But I do need to see how you guys set up those determinants for a 3x3 system. Okay. Now, I want you to stare at those 4 determinants, since now you have 3 variables, right? So you have a determinant for each of the variables. You also have a determinant, which stands for the denominator. Later on, it's going to go into the denominator. Do you see the same pattern as you saw in the 2x2 determinant? The way we set up those x and y, right? So let me highlight the column that probably bothers a lot of people. That is the constant column. See where they're going, right? And that tells you which determinant you're trying to get. All right, once you set it up, right? I mean, if you want, you can. Now there are tons of videos or different people explaining it different ways, like how to calculate the determinant, right? But you have calculator, right? Why would you not use it? But don't get me wrong, all right? So I'm not saying that you shouldn't know, but well, let me ask you, why do you think that they have calculator or a computer for us to use? Why do you think that people design calculators? Not just for learning, right? You know, you can use calculator or the fancy or the more advanced, you know, stuff of calculator will be the computer. If we have students, I'm sure that, you know, there are students like that can set up those determinants, like all of you should be able to do, right? But there are students who can just calculate those determinants following those patterns and get it done super quick, like in a minute, and get it all right. That makes them like a calculator, right? But what's the point of having real calculators if you try to do what the calculators try to do? And you know that there's no way you can beat the machine. Does it make sense? So, like I said, you know, we're preparing you guys for, well, a lot of you guys for the STEM route, right? You're not there get paid for doing those tedious work, right? But we designed the machine, right? So we know the Cramer's rule. Even Cramer's is not going to be ideal for the machine, right? But at least that we know what it is, and now we need to make sure that we are getting it right, because we know that as human beings we have our weak spots, which is, you know, getting all the detail to getting down to a perfection. Now, I want you guys to write down the D determinant and the X determinant for this 3x3 system, and calculate it if you want with the calculator, right? And I'll show you in a second. But first, write down the 2 determinants, D and X. Oh, Lucia. So yeah, so once you get that, I'll show you how to you know, quickly get it. It's just a simple click. And again, like I said, you know, for questions like that, you do get points for setting up those determinants correctly, not, you know, for the tedious work of getting them worked out. Okay. All right, so does everyone get something like that? DNX. All right, so now let's take out your calculator. And I'll also show you guys on the screen. There we go. All right, so again, we're going to use the matrix manual. Like I said, the determinant is just adds the value of the matrix. So go into second matrix, right? So I do have something typed up, but you can go in and change it to whatever you want. But unfortunately, they have, those preset letters. You don't get to choose D. Well, you can do D, right? Let's, choose the D for the D determinant, but you don't have X and Y or Z, right? Just go with whatever it is you want. But at least that we're gonna go to maybe the matrix D, right? Oh, we need to edit, right? Edit, then pick the letter D. Then we'll put in the dimension, which is 3 by 3, or order, right? 3 by 3. There we go, right? So now we're gonna type in exactly what you wrote as the D determinant, right? Just be careful with the negative sign. 3, 2, 3, and 3, -2, -1, then -1, 5, 2. All right, so let's see, 2, 1, -3, 3, -2, -1, -1, 5, 2, right? Okay, there we go. Once you're done with that, so let's do second quit, right? And let's specify the matrix X, right? So now you're gonna have to pick whatever letter you want. So let's go with letter A, right? So matrix A, right? I'll do 3 by 3. Oh shoot. Second matrix, we're going to edit, right? Then go fix the matrix A, 3 by 3. All right, so matrix X, right? So it's gonna be -12, 1, -3, 3, -2, -1, -3, 5, 2. Okay. See, -12, 1, -3, 3, -2, -1, -3, 5, 2. Okay, there we go. Right. So once you have the matrices stored in a calculator, again, second quit. So now let's call down the determinant. Second matrix, go to math, and the first option is determinant, DET. Hit enter. All right, so put in the matrix D. Matrix D. So we do second matrix, right? Matrix D is number 4, 5 and 4. Close the parentheses. Okay. Hit enter. -42. Okay. Now let's do the determinant of the X determinant, right? Second matrix, go into the math. First option, feed it with a matrix A from a computer, from a calculator. So second matrix, second math, second matrix. So that will be the matrix A. Okay. Close the parentheses. All right, and it works out as -42. All right, if it doesn't, that means you typed something wrong. So what do we get for X? It's -42 divided by -42. That will be 1, right? So that's the solution for X. You do that for the Y and the Z, right? You should get it. All right, so now 5 points, right, for an FRQ. 1 point for each determinant, 4 points. I have 1 point left. For what? for the solution. Right? If you get one of the solution wrong, doesn't matter whether X, Y, Z, right? That's wrong, so I'll take a point off. Okay? But there's no way you will miss that, right? So you don't get points for showing me the tedious math, right? So all the terms written out, there's no point of it. But if I see that the student put the constant column over here for the X determinant, I know there's something wrong, right? Because that's not what the rule says. Here's again, a very important question. I think that it's important than the math, since we don't even have to do the math ourselves anymore. Under what circumstances will a system of 3 linear equations about 3 variables have no solution in the sense of the Cramer's rule? Once again, under what circumstances will a system of 3 linear equations of 3 variables have no solution when you use the Cramer's rule? When d is 0 and when either of the variable matrix determinant is not 0, right? Because you will divide the variable determinant, X, Y, Z, you name it, by the d determinant. Well, d is 0, that's an indicator that something's wrong. Whether or not it's going to be no solution or infinite many, right? How do you know which case it is? You compute at least one determinant, whichever you want. I'll go with X, right? If X is not 0, that's no solution. But if X happen to be 0, 0 by 0, that's, it's not going to be a unique solution, right? And that will be infinite many. And for a 3 by 3 situation, you don't have to tell me what the solutions are, because I don't know what it is, right? Unless I do the matrix and find out what it is. You just have to tell me there's infinite many solutions, right? And again, I will figure out which to award you 5 credits, if there were questions that seem to be like trapped, right? So don't feel like that you have to get a solution for a system, whether it's 2 by 2 or 3 by 3. But you need to show me how to set things up, okay? And that's pretty much all you have to do about 9.5, right? So like I said, in the next couple of days, yes, homework is, of course, one of the things you have to get done. So take those questions from 9.5, right? Homework 9.5, play with the calculator, right? Get used to setting up the matrices and determinants. And the 2 packets I posted in the D2R announcements are the only sources that you better prepare you for the test, right? Test is next Tuesday. And that's it. Yeah.
It's showing like this, and then this is repeated on here.
Exactly. So that's one of the ways. Now, well, this is like, if you don't want to use the calculator, you want to calculate by hand, you copy the first 2 columns, put it on the side, do those things, right? And you can do it, but like I said, what's the point of that, right? It's on. So this is like, do you ever remember when you have to learn something, then you find your own way to help you remember? The word is mnemonic, right? That's a mnemonic. So people came up with a way, it happened to work. It's like, I used to write Chinese characters right next to, those English words. I want to make sure I pronounce it correctly, right? So, it's just, someone figured out a way to say, hey, if you do this, it works out. And if you look up on internet, so that's not the only way that works out. Ecuador.